This is the 8th video in this series dedicated to Bessey Shuffle diagrams. Recall, a shuffle S is said to be a Bessey Shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also, remember that we have color-coded the 8 position values as follows. Position values 1, 4, 6 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. The reason we do that is because of the structure of Bessey sequences, and that will become clear as we move forward, if that is a new concept to you. Also, we have this set of symbols here representing the situation where cards in positions 1, 4, 6, 7 remain somewhere in those positions, 1, 4, 6, 7, after a particular shuffle is performed. Similarly, the cards in positions 2, 3, 5, 8 also stay somewhere within those same position values. On the other hand, inversion occurs if the cards originally in positions 1, 4, 6, 7 get moved to position values 2, 3, 5, 8 in some assignment, and vice versa. When that happens, we say inversion has occurred, and we represent that outcome as follows. Finally, for a quick review, recall that Bessey sequences of order 8 have the following structure. So up above I have the 8 position values, and then down below I've indicated where zeros and ones need to be so that the sequence is a Bessey sequence. And there are just 2 possibilities. The ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. Alternatively, if we look at the inversion of this sequence, which is the one below, the role of zeros and ones switch places. The first new shuffle for today is called a judicious push-off of pairs, with stacking as indicated here. So let's go ahead and demonstrate this shuffle while simultaneously deriving its permutation. So we begin with an ordered packet 1 through 8 and perform our shuffle. Okay, so if you watched the previous video in this series, you've already been introduced to push-off pairs as a way to mix a packet of cards. Now the J here is for judicious, which simply refers to the fact that we will be stacking these in a way that's more complicated than just left to right or right to left. Okay? So push off pairs, how does that work? Well, you just push off the top 2 cards without changing their order, maintain their order as is, set those down, and then push off the next 2, set those down, push off the next 2, set those down, and then the last 2 go down last. Now the stacking is a leapfrog stacking that we've seen before. So pile 1, so this is pile 1, 2, 3, 4. Pile 1 leaps over pile 2 and gets stacked on top of pile 3. Pile 2 leaps over this pile and gets stacked on top of pile 4. So that's what we've indicated up here. And finally, in this particular mixing of the cards, we're going to stack the left pile on top of the right. Okay, so what is the new ordering of the packet? And from there, we can actually write a formal description of the permutation. So the new ordering is 1, 2, 5, 6, 3, 4, 7, 8. So using Cauchy's two-line notation, we obtain the following representation. The bottom row here is the new ordering that we've just demonstrated. So 1, 2, 5, 6, 3, 4, 7, 8. Converting this to cycle notation, we obtain the following. 1 goes to 1, so we get a fixed point, or a 1 cycle. 2 goes to 2. So whatever starts in position 2 ends up back in position 2. 3 goes to 5, so we have an arrow from 3 to 5. 5 goes back to 3, so we have this cycling back arrow. So this gives us a 2 cycle, or in other words, a transposition. 4 goes to 6, as we can see right here, and 6 goes to 4. So that completes a 2 cycle as well. 7 goes to 7, so it's a fixed point, or a 1 cycle. And 8 goes to 8, so we have another fixed point, or 1 cycle. Color coding, or cycle notation, of this permutation, we obtain the following. Now remember from our review, digits 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. So we get a single cycle, so the black 1 gets sent to itself, which means that the object in that position doesn't go anywhere. Red 2 gets assigned to itself, red 3 goes to 5, and red 5 goes back to red 3. Black 4 goes to black 6, which goes back to black 4. Black 7 goes to itself, it's a fixed point, and red 8 also gets assigned to itself, which is a 4th fixed point. So here we find the following. Each value gets sent to a value of the same color. So what this means then is inversion has not occurred. All of the cards that began in positions 1, 4, 6, 7, in other words, these 2 and the 2 in the middle, get moved back to somewhere among those 4 position values. The same thing with the cards that originally began in positions 2, 3, 5, 8. They return to position values contained in a complement. So in other words, we're looking at this situation here. Since inversion does not occur, we should be able to observe that with our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. So what it means is if we perform this shuffle, we will again get that same sequence form 1, 0, 0, 1, 0, 1, 1, 0. So let's go ahead and just demonstrate that. I'm just performing this judicious push-off pairs a second time. Remember, we're doing this leapfrog stacking. So 1 jumps over 2, lands on 3. 2 jumps over the 3rd pile and lands on the 4th. And then we're stacking the left pile on top of the right. So it should be the case that we get 1, 0, 0, 1, 0, 1, 1, 0, which we do. So that sequence form is preserved, even though we do know that the cards, or some of the cards, are moving around among themselves. Okay, so for example, the card in position 1 stays in position 1. The card in position 2 stays in position 2. But the cards in positions 3, which is right there, 3, and 5, which is right here, those 2 cards switch places. But of course we won't detect anything if both of them are labeled zeros. Similarly, the cards in positions 4 and 6, these 2 right here, technically traded places after this shuffle was completed. And then the cards that were in the last 2 positions, 7 and 8, are fixed points, so they did not go anywhere. Turning to our shuffle diagram, on the left, top row, we we find the following. We have these 4 fixed points, 1, 2, 7, 8, and then we have these double arrow lines between 3 and 5, and also between 4 and 6. So that is the Bessey Shuffle diagram for this particular shuffle. And we can see that this shuffle has order 2 because it's a product of transpositions. That means if we perform this shuffle twice, we return the packet to its original order. Our second shuffle is also a judicious push-off pairs shuffle, but this time we will stack the final right pile on top of the left pile. So let's go ahead and illustrate that. So as always, we begin with our ordered packet, 1 through 8, and we'll perform our shuffle. So this is a push-off, so you just push off the cards without changing the order of the cards within that pair. And push off the next 2 without changing their order, and the last 2. Now the stacking is the same as the previous one. It's a leapfrog stacking. So we're going to stack the first pile, so this is pile 1, 2, 3, 4. The first pile on top of the third, the second pile on top of the fourth, and then finally the right hand pile gets stacked on top of the left. So what is the new ordering of this packet after that shuffle has been completed? Well, let's take a peek. The new ordering is 3, 4, 7, 8, 1, 2, 5, 6. So expressed in Cauchy's 2-line notation, we obtain the following. The top row, as always, is 1 through 8, and then we simply list the new ordering of the cards. 3, 4, 7, 8, 1, 2, 5, 6. Converting this to cycle notation, we obtain the following. Note that 1 goes to 3, so we have an arrow from 1 to 3. 3 goes to 7, so there's an arrow from 3 to 7. 7 goes to 5, so there's an arrow from 7 to 5. And then 5 returns back to 1, so that completes that cycle. And this cycle is of length 4. This is called a 4 cycle. Continuing on, we see that 2 goes to 4, so we have an arrow from 2 to 4. 4 goes to 8, an arrow from 4 to 8. 8 goes to 6, an arrow from 8 to 6. And then 6 returns back to 2, completing a second 4 cycle. Color coding these position values, we obtain the following. Remember, position values 1, 4, 6, 7 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. Using that convention, we get the following. Black 1 goes to red 3, which goes to black 7, which goes to red 5, which cycles around to black 1. In our second 4 cycle, we get red 2 goes to black 4, which goes to black 6, which cycles back to red. So here, each value gets sent to a value of the opposite color. Consequently, inversion has occurred. This simply means that the cards that originally began in positions 1, 4, 6, 7 have moved to positions 2, 3, 5, 8 after the shuffle, and vice versa. Cards that originally began in positions 2, 3, 5, 8 get moved somewhere to positions 1, 4, 6, 7. So there's been kind of a wholesale exchange of the cards in those 8 positions. And consequently, we would represent this situation as follows. A goes to A complement, and A complement goes to A. Since inversion occurs, we should be able to detect that applying this shuffle to the Bessey sequence 1001, 0110. And so what should happen is we should obtain the inversion of this sequence, which will be 0110, 1, 0, 0, 1. So the zeros and ones simply trade places. Okay, so let's go ahead and just perform this shuffle again. So we're pushing off pairs. So you just push off 2, push off 2, push off 2, and then push off 2. The stacking is this leapfrog stacking. So this pile 1 leaps over pile 2 and lands on top of pile 3. Pile 2 leaps over what was pile 3 and lands on top of pile 4. And now here we're stacking the right pile on top of the left. So what should be the case now is the sequence that we started with should be, quote, inverted. In particular, that means we should now have 0, 1, 1, 0, 1, 0, 0, 1, which we do. Now, it is true that the zeros and ones are moving places. In fact, all of them have moved to new locations. And that's evident by our representation of the permutation. We have no fixed points this time. So every single card has moved to a new location. And the shuffle diagram for shuffle 30 is the following. So we see that 1 goes to 3, which goes to 7, which goes to 5, which wraps around and goes to 1. So if we begin at 1, there'll be an arrow from 1 to 3, which there is, an arrow from 3 over here to 7, and then from 7 down to 5, and from 5 back up to 1. So that completes that 4 cycle. We also say that the values 1, 3, 5, 7 in that cycle constitute an orbit, or that they are members of the same orbit. Similarly, for this 4 cycle, 2 goes to 4, which goes to 8, which goes to 6, which goes back to 2. So if we begin at 2, there should be an arrow from 2 down to 4, which there is. There should be an arrow from 4 up to 6, which there is. And there should be an arrow from 4 to 8, which there is. From there, an arrow from 8 to 6, and then an arrow from 6 back to 2, completing that 4 cycle. So those 4 values, 2, 4, 6, 8, also constitute a second orbit, since they just move around among themselves each time this shuffle is performed. And as we'll see in just a moment, shuffle 30 is the inverse of shuffle 32. Okay, and we'll demonstrate that in just a moment. Our third shuffle for today is shuffle 31, which is also a judicious push-off pairs. So let's go ahead and illustrate this shuffle and derive the permutation associated with it. So we begin with the ordered packet 1 through 8, and we perform the shuffle. Recall, a push-off pairs is where you just push off the top cards without rearranging the relative order and just set them down as one pile. Push off the next 2 and just set them down as a second pile. The next 2 as a third, and then the final 2 as a fourth pile. And that's how we number the piles, 1, 2, 3, 4. Now the stacking this time is we're going to use this leapfrog stacking. We're going to leap over the neighbor of one pile and land on another pile. So here, if we read the notation, pile 4 will be set on top of pile 2, pile 3 will be set on top of pile 1, and finally, given those 2 piles, we will stack the right-hand pile on top of the left. So that is this new shuffle here. Okay, so let's go ahead and do it. Use this leapfrog. 4 goes on top of 2. 3 goes on top of 1. And then we're stacking the right pile on top of the left. So what is the new ordering for this packet? And what would the Cauchy 2-line notation be for this permutation? So the new ordering is 7, 8, 3, 4, 5, 6, 1, 2. So in Cauchy's 2-line notation, we obtain the following. We begin with the top row, of course, just being 1 through 8. And then the second row will be the new ordering that we just found. 7, 8, 3, 4, 5, 6, 1, 2. So that is Cauchy's two-line notation. This two-line notation can be converted to cycle notation, also called one-line notation, as follows. We just look at what happens with each position. So 1 goes to 7, so there's an arrow from 1 to 7, and then 7 returns back to 1, so it cycles around. So we get this two-cycle, also called a transposition. What happens with 2? Well, 2 goes to 8, so we have an arrow from 2 to 8, and 8 returns back to 2. So we get a second transposition, or two-cycle. Now, 3 gets sent to 3, so we have a fixed point. This is also called a one-cycle. 4 goes to 4, it's also a fixed point then. 5 as well, and 6 as well. So that accounts for all 8 digits. Now, I do want to remind the viewer that normally when we write a permutation in cycle notation like we have here, we don't include the one cycles, the single cycles, as long as it is clear as to the size of the set we're working with. So as long as we know that we have 8 distinct objects, then we can drop these one cycles without losing any information. So in other words, what it means is any number between 1 and 8 that's not present here in either transposition would have to be a fixed point, which they are. If we color code our position digits, we obtain the following. Remember, the positions 1, 4, 6, 7 are color coded black, and position values 2, 3, 5, 8 are color coded red. And this aids us in discerning what effect a particular shuffle has had on the underlying Bessey sequence structure. The two cases being that it returns the sequence to the same form of the Bessey sequence, or it converts it into its inversion. Okay, so we see that black 1 goes to black 7, which returns to black 1. Red 2 goes to red 8, which returns to red 2. Red 3 gets assigned to itself. Black 4 gets assigned to itself. Red 5 gets assigned to itself. Black 6 gets assigned to itself. So here we have the following. Each value gets sent to a value of the same color. So we do not have an inversion of the sequence in this particular case. So what that means then is if we start with our quintessential Bessey sequence of 1, 0, 0, 1, 0, 1, 1, 0, and perform this shuffle, we should get that sequence form back. So why don't we go ahead and perform it again. So I'm just pushing off the top 2, setting those down, pushing off the top 2, next 2, and the bottom 2. The stacking, as we see here, so we're picking up the 4th pile first, it's leaping over the 3rd and landing on the 2nd. Here we pick up the 3rd pile, if I can get underneath it, and it jumps over the 2nd and lands on the 1st pile. And then here we're stacking the right pile on top of the left. So what should happen here is we should get back to the same sequence organization, namely 1, 0, 0, 1, 0, 1, 1, 0. And we do. Now, it is important to realize that some of these cards labeled with a 0 or a 1, some of them have stayed right where they were, and others have moved, even though it's hard to tell because we have the same labeling. So in particular, the cards originally in the 1st position and the 7th position, this position and the 1st position, they've switched places. The cards originally in position 2 and 8, way over here, those have switched places. All of the other cards have stayed where they started. So in this case, we would say that this shuffle preserves Bessey sequences. And what that means is, if you start with a Bessey sequence of this form, you end up with a Bessey sequence of this same form. 1, 0, 0, 1, 0, 1, 1, 0. We can see that since this shuffle is a product of transpositions, it has order 2. So performing this shuffle twice returns the packet to its original order. And if we look at the shuffle diagram for this shuffle, we find the following. Because 1 and 7 constitute a 2-cycle, we should expect to see a double arrow between 1 and 7, which we do. Also, the transposition or 2-cycle 2, 8 would lead to a double arrow between 2 and 8, which we have. All of the other values have been left as they are, indicating that they are fixed points. The objects in those positions are returned precisely to those same positions, so they do not move anywhere new. And we can see right here that inversion does not occur. Our fourth and final shuffle for today is also a judicious push-off pairs with the stacking similar to the previous shuffle, Shuffle 31, except that the final 2 piles will be stacked with the left pile on top of the right. So let's go ahead and illustrate that and derive the permutation associated with this shuffle. So we begin with our ordered packet 1 through 8, and we perform the shuffle. So push-off pairs is where you just push off the top 2 cards without rearranging the order of those 2 cards relative to each other. You push off the next 2. You push off the next 2. Finally, that leaves us with 2 that would make up the 4th pile. So we have piles 1, 2, 3, and 4. And so we can see the stacking requires us to do the following. This is pile 4. It leaps over pile 3 and gets stacked on top of pile 2. Pile 3 leaps over pile 2 and gets stacked on top of pile 1. And now we're going to stack the left pile on top of the right. So what is the new ordering that results from this shuffle? Well, it's the following. 5, 6, 1, 2, 7, 8, 3, 4. So writing this in Cauchy's 2-line notation, we obtain the following. The top row, as always, is just 1 through 8. The bottom row will be the new ordering, 5, 6, 1, 2, 7, 8, 3, 4. And we can convert 2-line notation to cycle notation, in other words, 1-line notation, as follows. We see that 1 goes to 5, so there's an arrow from 1 to 5. 5 goes to 7, so there's an arrow from 5 to 7. 7 goes to 3, so we have an arrow from 7 to 3. And 3 returns back to 1, so that completes that cycle. And in particular, it is a 4-cycle, since it consists of 4 position values. In a similar fashion, let's see what happens with 2. 2 gets sent to 6, so we have an arrow from 2 to 6. 6 gets sent to 8, so we have an arrow there from 6 to 8. And then 8 goes to 4. We can see that with the arrow. And then 4 returns back to 2, completing a second 4-cycle. And that accounts for all 8 digits. So if we color code our digits, we obtain the following. Recall that positions 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. And as we've talked about, this will aid us in perceiving the effect of shuffles on Bessey sequences of order 8. So we see that black 1 goes to red 5, which goes to black 7, which goes to red 3, which wraps around and goes to black 1. Red 2 goes to black 6, which goes to red 8, which goes to black 4, which gets sent back to red 2. So each value gets sent to a value of the opposite color. And when that happens, inversion has occurred. Now, this simply means that the cards that originally began in positions 1, 4, 6, 7, so in these 4 positions, 1, 4, 6, 7, those cards get moved to positions 2, 3, 5, 8 in some assignment. Okay, and in a similar way, the cards that originally began in positions 2, 3, 5, 8 get moved to positions 1, 4, 6, 7. And since inversion occurs, we should be able to detect that using our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. Because apparently this shuffle should invert this sequence. What does it mean to invert the sequence? That means that zeros and ones switch places. So let's see if that actually occurs. So we're going to perform our shuffle. So we push off the top 2, push off the next 2 as a second pile, the next 2 as a third, and the final 2 as a fourth pile. And the stacking is the fourth pile gets stacked on top of the second, the third pile gets stacked on top of the first, and then the left pile is stacked on top of the right. Okay? So is it true that inversion has occurred? Well, inversion will have occurred if we now have the sequence 0, 1, 1, 0, 1, 0, 0, 1, which we do. And it's important to note that the zeros and ones in our packet here, all of them have moved to new locations, as indicated by our cycle notation of this permutation. There are no fixed points whatsoever, so every single card is moving to some new location according to these assignments here. And also note that this particular shuffle is of order 4 because it's a product of 4 cycles. That means you need to perform this shuffle 4 times to return the packet to its original order. And finally, taking a look at the shuffle diagram for shuffle 32, we find the following. 1 goes to 5, which goes to 7, which goes to 3, which wraps around to 1. So that means if we start at 1, we should have an arrow that goes from 1 to 5, 5 to 7, 7 over here to 3, and then an arrow from 3 to 1, completing that cycle. And we say that those 4 values are members of the same orbit. In a similar fashion, for the second 4 cycle, we see that 2 goes to 6, which goes to 8, which goes to 4, which gets sent back to 2. So that means if we begin at 2, there should be an arrow from 2 to 6, which there is, from 6 to 8, which we have right here, from 8 all the way down to 4, and then from 4 back to 2. And that completes that 4 cycle. And those 4 values represent a second orbit. And as I mentioned a few moments ago, shuffles 30 and 32 are inverses of one another. If you perform them in succession, they will return an ordered packet to its original order. Why don't we just go ahead and illustrate that quickly, since these two do constitute an inverse pair. So if we begin with our ordered packet, so that we can keep track of what effect these shuffles will have on the starting packet, what we have just observed is that if we perform, let's say, shuffle 30 first, followed by shuffle 32, it should return this packet back to its order 1 through 8. And vice versa, if you perform shuffle 32 first, followed by shuffle 30, it will also return or reset the packet to its original order. So why don't we go ahead and perform shuffle 30. So it's a push off pairs, so we're just pushing off pairs without changing the relative order of the cards within each pair. And then if you look at shuffle 30, it's the top row on the right. We're stacking the first pile on top of the third, the second on top of the fourth, and then we're stacking the right pile on top of the left, like so. Now, of course, we're going to get quite a mixture of cards here, right? We get 3, 4, 7, 8, 1, 2, 5, 6. This is very different than 1, 2, 3, 4, 5, 6, 7, 8, okay? But what we have just seen is now if we perform shuffle 32, it will straighten all of this out and take us back to our originally ordered packet 1 through 8. Now, if you look at the differences between these two shuffles, I don't think it's clear, and probably would not be clear to most anyone, that these shuffles should undo the effect of each other. I don't think that's clear at all. So shuffle 32, we begin the same. We push off pairs, but this time the stacking is different. We're going to stack the fourth pile on top of the second, the third one on top of the first, and now we're going to stack the left pile on top of the right. And apparently this will perfectly undo the effect of shuffle 30, which it does. It returns the packet to its original order 1 through 8. Okay, as an application, I have here 4 numbered cards and 4 face cards of different colors and suits. So what we're going to do is I'm going to mix these cards, since both of us just saw them, and I'm going to do this kind of triangle deal, which is kind of a fun way to mix cards. And we'll just stack them in the opposite order, which will help to randomize the cards well. Okay, so what I need you to do is kind of randomly choose one of these new shuffles for us to perform first. So which one would you like? Shuffle 30? Okay, so all of these are push-off pairs shuffles. Okay, so I'll do that. Very good. So shuffle 30 is as follows. Pile 1 goes on top of pile 3. Pile 2 goes on top of pile 4. And then the right pile gets stacked on top of the left. Okay, so that is shuffle 30. Which one would you like next? Shuffle 31? Okay, shuffle 31. So we push off the pairs as before, and the stacking will be a little different. So for shuffle 31, the stacking is the fourth pile goes on top of the second, the third one goes on top of the first, so you can think of this as a leapfrog stacking, and then the right pile goes on top of the left. Very good. Okay, so we have 29 and 32 left. Which one would you like? 32 next? Okay, so I'll push off pairs as before, and so shuffle 32, we're going to stack the fourth pile on top of the second, third on top of the first, and now we're going to stack the left pile on top of the right. Very good. Okay, and so to finish, we're going to perform shuffle 29. I believe it's the only one we haven't done yet. So we'll push off pairs, as always, and then for shuffle 29, we see the following. We stack 1 on top of 3, 2 on top of 4, and then we stack the left pile on top of the right. Now, it's very important for you to realize that not only could we perform any of these shuffles additional times and in any order, we can actually perform any of the 32 shuffles that we have shown you thus far in this series. And we can perform them in any quantity and in any order. And it will not undermine what we hope to accomplish here. That's the amazing thing. Okay, so what we're going to do here is we'll go ahead and perform this kind of fun triangle deal to just further scramble these cards so that no one could possibly know where anything is. And then I think I'll go ahead and I guess we could continue mixing if you would like, or if you're finished, we can stop now. Okay, so you're a bit tired? Stop now? Okay. So what I'm going to do is I'm going to set out 2 piles here. Let's see. Yeah, that's 4 and 4. And I'll give you the choice to choose either pile. You'd like this one right here? Okay, very good. And that leaves me with the ones right here. Very good. Oh, by the way, I have a prediction over here. I had almost forgotten that I set it there. So what does our prediction say about the ending of all of this? It says one player will have one black face card and 3 number cards. And the other player will have one black number card and 3 red face cards. I wonder if that's true. So let's take a look at what you got here. Okay, so you got a red face card. So in fact, I guess for this to be correct, you better be down here. Oh, you got 2 red face cards. Black number card. Okay, so we haven't blown up the universe yet. Oh, look at that. You got 3 red face cards and 1 black number card. Amazing. Well, I would imagine, kind of by an elimination process, my pile probably satisfies the other set of outcomes here. So apparently I'll have 3 number cards and 1 black face card. Is that true? 3 number cards, yep, and 1 black face card. How in the world were we able to finish in such a way that this prediction that was written ahead of time, before the randomization of the packet dictated by you, the spectator, how in the world were we able to perform such a perfect sequence of actions that would agree with a prediction that was written before we even started? Okay, so let's talk about how this was done, and many variations on this that you could actually use. Okay, so what I did at the beginning, and so you can rewind the video and see this. So what you do is you need to have these 3 piles, right? These 3 piles that will satisfy your prediction. So you need that first. So you need a little pile of 4 cards in which you have 1 black numbered card and 3 red face cards. And then you need a little pile of 4 cards in which you have, move this up, 3 red number cards and 1 black face card. Okay, so you need that. You need like these 2 halves. These 2 piles of 4 cards. Now, within each pile, these can be randomized. It doesn't matter what order these are in. The same thing here. Now, what will be important is that you just stack them as sets of 4. So I can put this one on top of that one, or vice versa. That stacking doesn't matter, actually. Okay? So right now, if you think about it, the organizational structure that we kind of have in mind here is I'm picturing, let's say, the cards on the top half of this packet of 8 cards as 4 ones. It's like 4 ones. And then the bottom 4 cards I'm picturing is labeled zeros, with zeros. Okay? So in your mind's eye, if you kind of want to think about that, so kind of picture the top 4. Imagine labeling these all ones, and the bottom 4 are labeled with zeros. Okay, so these are all part of the same set, which in our mind's eye we're labeling as zeros, and the top 4 are all part of the same set, which in our mind's eye we're labeling as ones. Okay, so that's kind of where we're beginning. Now this structure type can be converted to a Bessey sequence using this triangle deal. Now this is a really clever little technique by Werner Miller, who's one of my subscribers, and he came up with this very clever way of going from this organizational structure to a Bessey sequence. Okay? So if you use this triangle deal, and you'll recognize now that I did it. I did this 1, 2, 3, 1, 2, 3, 1, 2, and then you stack in the opposite order. So we dealt clockwise, and then you pick up the first pile again, but now stack in counterclockwise direction. Okay, so what this will do then is it will actually convert this to, quote, a Bessey sequence relative to the labeling up here. Okay, now it gets pretty difficult to kind of see that now that we have them scrambled a bit, but it's not too hard to recreate it because focus. Remember, special positions are 1, 4, 6, 7, and 2, 3, 5, 8. So why don't we focus on 1, 4, 6, 7? So position 1's right there. There it is. Position 4 is the king right there. Positions 6 and 7, let me move that out of the way, is right there. So look at what are in these positions. We have a black numbered card and then 3 red face cards. Okay, that was the designation of the cards at the bottom of our sheet. We have 1 black numbered card and 3 red face cards. Now what that would leave us then for, quote, zeros, which are in positions 2, 3, 5, 8, will be the other half of this prediction. Namely, we were looking at a red 6, a red 8, a red 3, so 3 red number cards, and then a black face card. Okay, so this is truly a Bessey sequence relative to those 2 sets of cards that we want to finish with at the very end. Well, since it's a Bessey sequence, what that means then is you can perform any of these shuffles that we have taught you so far in any order and in any quantity, and it will not undermine the fact that this is a Bessey sequence. Now, it may invert it, right? You remember what the inversion is. The inversion is where the zeros and ones switch places. So we may invert things. In fact, we can probably just remind you which one does that. If we actually perform these 4 shuffles exactly once, we will end up not inverting the packet because look, shuffle 29 does not invert it. Shuffle 30 does invert it, so it's inverted. Come down here, shuffle 31 does not invert the current structure, but shuffle 32 inverts it a second time. So the inversion of the inversion, you're back to where you were. So if we perform each of these shuffles exactly once, we actually return this back to its original organizational structure. Now that's not really important to keep track of. I guess I should make that clear because I don't want to overwhelm you, because the way that our prediction is written, we're not stating who receives each pile of 4 cards. We're just saying one player receives these 4 and the other player receives those 4. Okay, so that does simplify things for you if you're not wanting to keep track of whether inversion has or hasn't occurred. Okay, so that I did that just to keep the performance as simple as possible. But if you want to go a little deeper, knowing whether the packet is inverted from where it started is important. Now, I do want to point out, however, that you can always peek the bottom card. So if after all the shuffling has been done that the spectator calls for, and you just surreptitiously glance the identity of the bottom card, you could deduce whether or not inversion has or has not occurred. Okay? But since we're not worried about inversion occurring, since it has no effect on our prediction, we won't worry about that right now. Okay, now the point I wanted to now make is, now that we've mixed it, we've performed those 4 shuffles, the way that we go back from the Bessey structure back to this organization is you just perform the triangle deal again. So that is something taught in the videos on this playlist that are devoted to Bessey sequences. So if you do the triangle deal again, you will essentially separate the cards so that the top half and the bottom half correspond to these separate outcomes written on our prediction page here. Okay? So, and I believe that's what I did. I said, okay, well, why don't we just further, we'll just kind of further scramble the cards one more time. So I did the triangle deal. And then if you stack in opposite order, what that means is it's back to this kind of arrangement, where the top four are of one kind and the bottom four are of the other kind. And we'll see that in just a second. Okay? Now that's just one way to kind of separate the cards into two groups of four. And if you're willing to add one or two more elements to the mixing of the cards, we could eventually end up with an alternating packet that could be dealt out first to you, then me, you, me, back and forth, and still end up giving you a special set of 4 cards, and I receive the other special set of 4 cards. Okay, so anyway, this is just one way to perform all of this. And so let's go ahead and just check. So what we would normally do after this point, we'd say, oh yeah, I have a written prediction here. Let's see, what does that say? Let's see, it says one player will have 1 black face card and 3 red number cards, while the other player will have 1 black numbered card and 3 red face cards. Is that true? Let's just check this. Okay, let's just see if this is true. Oh wow, check that out. Does that match here? So I have 1 black number card, that's true, and 3 red face cards. How in the world did we do that? And so what does that leave here for me? Well, it better be the case that I received 1 black face card and 3 number cards. There's a red number card. There's a black face card. There's a second red number card and a third red number card. Indeed, our prediction perfectly anticipated the ending for this randomization of these 8 cards, and then just a dividing of the packet of 8 into 2 halves. How did we do that? Well, you know how we did it now that I've shown you what's going on, of course, right? Okay, so that's just a kind of simple application using Bessey Sequences and Bessey Shuffles, and in particular these new shuffles that we're showing you today, shuffles 29, 30, 31, and 32. So thank you for watching, and take a look at some of the other videos on the Hidden Structures channel, as well as the next video in this particular series.